From our first breath of the day, to brushing our teeth, to washing our faces, our first sips of coffee, and even in the waters of the rivers we have built cities upon since antiquity, we find ourselves surrounded by fluids. Fluids, in this context, mean anything that could take the shape of their containers. Physically, that means that anything that has molecules that can move past one another. But mathematics has, as always, a slightly different view. This view is seen by some as more nuanced, others as more statistical, but by all as a challenge. This definition cannot fit into an introduction, and we will be picking away at it for the remainder of this episode. So what is a fluid? What can we learn from it? And how can learning from it be worth $1 million? All of this and more on this episode of Breaking Math. Episode 17, Navier-Stokes. And now we'd like to take a quick moment to announce our sponsor, Brilliant.org.
You may have noticed that we're diving into a lot of calculus in this episode, and while we hope we do a good job of explaining it, you may like to dive deeper into those topics.
And that's what Brilliant.org can help you with. They have courses on everything from calculus to other topics like trigonometry and even general problem solving.
I actually used it a lot when I was teaching 7th grade math too, that they have a lot of really fun problems on very specific topics. Like we could go to the standards that we were on and use some random problem from Brilliant. It was awesome.
And they help you with the answers, so it's more like tutoring too, which is something that I am very familiar with.
Well, and the wiki is really cool that you can see other people's answers and analyze whether or not they know what they're talking about, which is a really good learning experience because sometimes they're just full of crap. But most of the time it offers a really good discussion.
Oh yeah, definitely. It's a wonderful website.
So if you'd love to learn, and we know you do because you're listening to us, if you'd like to support the show, please check out brilliant.org/breakingmath.
There's nothing to lose but your ignorance. Can we say that?
Sure.
Good. Now back to the show. I'm Jonathan Baca.
And I'm Amy Lynn, filling in for Gabriel Hesh, who's out on important business today. So what are we going to be talking about today?
We're going to be talking about the millennium problems on a series of episodes. And today we're going to be talking about the Navier-Stokes equations. I'm going to warn you that this is going to be a little bit of a scary episode for some of you. We're going to be talking about calculus, vector calculus, and even differential equations.
But don't turn off the podcast. We're going to break down each of these concepts so that they're easy to understand. Well, easier.
Yeah, so these problems are worth solving just in the world of math, but they're also worth solving in the world of, I guess, money.
Yeah, there's $1 million prize, right? If you solve one of the millennium problems.
Yeah, it's the Millennium Prize problem set by the Clay Mathematics Institute in 2000. It was following a tradition from the century before. 6 have yet to be solved as of 2017. Only 1 has been solved, as far as I understand, and I think it's a very complicated proof from what I've heard.
Lame. I like the easy proofs. Well, not easy, but elegant. What I would say. So, okay, so let's talk about the Navier-Stokes. I'm sorry, I keep saying it the American way. Is it Navier-Stokes?
I believe it's Navier-Stokes, but
it's French.
I'm American as well.
Okay, so we'll alternate between trying to say it correctly and just going with what comes out. So what are the Navier-Stokes equations? What would a solution to those mean?
We do understand and we know how to model things based on the Navier-Stokes equations. When you're modeling fluids for 3D simulation, you do something, it's roughly based on the Navier-Stokes equations, sometimes Euler equations, which we'll be looking at later. But a solution would mean simplifying them significantly. It would allow us to predict weather a lot better. It would mean more efficient hydraulics, new types of machines that we haven't even dreamt of, and it would even possibly mean a solution to the problem of turbulence, which Feynman called the most important problem in classical physics.
I've taken, I think, 2 classes in all of my math. One was specifically called geophysical fluid dynamics. I don't feel like I learned very much from it, but I do remember being kind of blown away by how difficult it is to mathematically model fluid motion. Like, it doesn't seem like it would be that complex, but it's unbelievably complex.
Oh yeah, and I think maybe a little intuition as to why this is so complex is if you've ever been in a pool, and if you've ever dropped a pool toy in a pool, like even a ball, it doesn't take a straight path towards the ground. It wiggles around and wobbles. It follows a very complex motion, and that's just a ball. When you're just dealing with no air, like in ideal physics problems, you can predict where the ball is going to be in 100 years. So we're going to be talking about these amazing equations, where they came from, where they are, and where they're going.
And a little bit about why we care about them.
Cities are often built on rivers. Agriculture, beyond a small scale, depends on the mobilization of water, and boats travel very efficiently. For these reasons, and probably others, humans have always studied the mechanics of fluids. It is in this history that we see how the idea that would eventually become the Navier-Stokes equations took form. So, I think one of the first fluid dynamics, would it be fluid dynamics or fluid mechanics, was invented or discovered by Archimedes of Syracuse.
Is that the where he submerged the crown to figure out volume?
Oh yeah, and I think we should go back a little bit and discuss how that worked and why that worked. Just really quickly. Do you want to tell the legend?
Well, I only have a cursory knowledge of it, that he was able to determine the volume amount of gold in a crown by submerging it in water and measuring the displacement.
Yeah, he what he did was he put the scale itself underwater and weighed it with he weighed an equal amount of gold above water where air is very light, so you can't tell the difference. Mm-hmm. And when he submerged the two, the gold and the crown had different buoyancies. So that's how he saw that the crown was not made out of pure gold, and the man was executed.
See, I hadn't heard that part. I guess we just got the boiled down version that didn't involve murder in elementary school. Just the part about you can put things in water and figure out how much volume they have.
It's not ancient Greek history without a little bit of murder.
That's true. That is a fair point.
And what's really important, I think, about this, and tell me if you agree, is that for the first time you have a little bit of calculus, the amount of volume displaced by the water, volume itself being like a principle closely related to calculus, and you have physics related to that, the amount of force that is caused by the buoyancy.
Well, I think it's kind of a stretch to say that it's related to calculus, because I feel like, at least in my mind, calculus is the math of movement, and I don't know that there's a direct analogy, but I suppose there's rate of change of displacement. But it's one of the first we're trying to scientifically measure something or do it in an entirely different construct than had been previously done before, and I think that creativity is certainly the foundation of a lot of mathematics.
And one interesting thing that he actually did with his principle of buoyancy is a sort of proto-calculus where he would divide shapes into a bunch of different slices that had levers submerged in different amounts of water. You can actually read it online, The Method of Mechanical Means. We don't have time to go into that.
See, that sounds a lot more like calculus.
Yeah, he would prove everything with calculus and then reprove it with traditional Greek geometry.
Traditional Greek geometry was a lot of work. It was cool, but it was a lot of work.
Oh yeah, it's definitely different than the sort of math that we have since, I guess, the 1800s.
Mm-hmm. Certainly the geometry we have since then. We don't do it I feel like the Greek geometry was much more philosophical and logic based, and now it's a lot more about like, what's the circumference?
And maybe that's why Hero of Alexandria invented the first steam engine and never did anything with it. He called it the Heliopile. It was steam that made this ball rotate very, very quickly. It's not like he didn't know that he could do anything with it. He invented a wind wheel, but he did nothing with the Heliopile. We could have had steam engines for 2,000 years now.
I wonder if it was like his Van de Graaff generator, that it was just a cool thing he had in his office in the background to make him feel like he was a cool scientist.
Oh yeah. I mean, I do know that Hero of Alexandria, one of his things was like he had a coin-operated holy fountain water thing. It was a lot of novelty things.
All right, so he was a jokester. Guess he couldn't sell that one.
So basically, between then and about 1,000 years later, there's not much fluid dynamics or fluid mechanics that was really invented. But I think, and I just discovered this person while researching for this episode, and I think that I'm going to try to pronounce his name. His name, I think, is Badi Az-Zaman Abu Iz ibn Ismail ibn Ar-Razaz al-Jazari.
Your internet was not blocking out. That's just how many syllables there are.
And I've probably butchered that. I know we have some listeners in the Middle East. If you could write in and tell us how well I did, that would make me feel very good.
I think from now on we'll just call him Al-Jazari.
All right, yeah.
We'll go with that might be too white or too American, but we're going to go with the very last name because we can pronounce it more than anything. So I'm looking at the list of things you have printed here. He's done about a dozen amazing things. It's 8, but it's close to a dozen.
Oh, yeah. I mean, he invented, or at least not necessarily invented, but refined the camshaft and the crankshaft. He invented a chain pump, which is an improvement over the traditional Archimedes screw that everybody learns about in elementary school. And that was to provide irrigation. So and this was actually a chain pump driven by water itself. So he basically diverted a river uphill, which is a really cool feat in my opinion.
Yeah, super helpful. So where was he?
He was, I believe, Baghdad.
Okay.
If I'm wrong about that, then I will feel very bad.
And time frame, do we know?
About the Golden Age. So I think about the 8th century, 9th century, somewhere around there.
Nice. That is. I have no idea what a camshaft is. Is that embarrassing? I don't know what that is.
Camshaft, I believe that's it moves. It translates rotational motion into sinusoidal linear motion. Like a pin or a rod up and down with
rotation.
With the tooth. It's basically an off-center wheel that moves a pole, and it's useful for all sorts of things.
Is that similar to what's the one that's in the water? The
water wheel?
Maybe. Is that what it's called? Is that all it is?
I think it's what it's called.
Water wheel. I mean, that's usually the grain and refineries back in the 18th century, 17th century.
Oh yeah, a camshaft is more like let's say you needed to have like a pounding motion for some reason, or so instead of being a direct, like a very steady motion, it's a quick up and down motion that's caused by rotational motion.
Okay.
So this is the kind of cool stuff that Al-Jazari was bringing to the table. He also had one of the cool things is he built an automatic waitress who would come out through a set of doors, pour tea from a selection of teas and liquors, and go back. So, I mean, he probably had a lot of money at his disposal, but he did some cool things with it.
That reminds me of Doc Brown in Back to the Future 3 with his giant machine that built ice.
I'm not familiar.
You haven't seen Back to the Future 3 where he goes back to the West?
I thought there was only one Back to the Future movie.
Oh my God, there's 3. What have you been doing with your life, Jonathan?
I've been writing this outline.
Oh, well, fair enough. You need to, I think for the next episode, you need to go watch all of the Back to the Future movies. You're missing out.
Will do.
All right, so we're in the 8th century, is that what you said?
Yeah, but we're going to fast forward all the way to the 17th.
Does that mean my favorite? Is that Newton and Leibniz?
That is, and specifically Newton this time.
Yeah, the physicist.
And one thing that he studied, he studied everything, but including alchemy, but was the friction caused by water. So this is an essential component of how fluids interact. There's, I think we should talk a little bit about the properties of fluids before we go on.
We should probably also mention friction. That I think everyone's familiar with friction in the sense of when you get a rug burn, that's from friction, right? That you scrape your skin over the rug, and there's heat that comes from the friction of the movement on the floor. I didn't realize. I mean, I guess I did. Technically, I did. That there's friction in fluids.
Oh yeah, I suppose anything that translates, anything that can slow down creates heat through friction, I guess. And I guess fluid is no exception, even though, and I'm not sure if it was Newton who did this experiment, but someone showed that stirring water made it warmer. So not sure if that was before or after Newton, but that's one way of showing that friction is even though it's much less part of, I mean, we use lubricants all the time for things like doors, but there's still friction involved. You can't get rid of it completely.
Well, that's why all the physics classes when you're in high school say, presume a frictionless surface, because it's just too complicated to include friction in our calculations.
Oh yeah, you with nonlinearity. If you listen to the episode "Wreaking Chaos," you get a chaotic system with certain degrees of nonlinearity, which are very easy to come across when you add things like friction and viscosity. It's the resistance to shear stress. Shear stress being when you rub your hands together, you have shear stress between the two, or when you twist a pencil apart. There's a little bit of shear stress there. So you'll notice if you have what's a viscous fluid? Soap. When you get soap, when you push it, a lot of it moves with it, and only liquid hydrogen and I think some bizarre physical things are actually inviscid fluids.
Well, liquid nitrogen, how could you even tell? It evaporates
Oh
instantly.
no, liquid helium.
Liquid helium, okay.
Yeah, so it's...
well, I feel like that'd be a similar issue. Because it would evaporate before you could even, like... Could you get something cold enough to be able to determine its viscosity?
Oh yeah, well the reason why you could tell it's inviscid is because the vortices that it forms don't stop. Oh. So you can stir it and it'll keep going forever.
That's awesome.
Yeah, so if you ever need a cup of coffee, make it with liquid helium.
You'll sound funny too when you drink it.
Yeah, and that's the only bad thing that'll happen.
I feel like you'd have like an eternally flushing toilet with liquid helium. You'd never have to flush it. It'd just keep on going.
And that's actually a very odd way of bringing up one important thing about fluid dynamics is that they do not violate Newton's laws or any laws of conservation, even though they may seem to. And the reason why is you can think about it this way. If you have a train that's going around on a circular track, if you're on the train already, it takes very little energy to get to somewhere else, but to get off the train is what takes energy. So it's only change in rotational energy or rotational movement that takes energy, at least in certain contexts.
So staying on the merry-go-round isn't hard. It's getting off of the merry-go-round that's hard.
Oh yeah, and starting the merry-go-round, like there's definitely something about the difference between rotational and linear motion but I think that's a philosophical thing for another episode, definitely.
Well, and it's all about perspective too, right?
Yeah, physics is all about what you make it.
Although my students try to use arguments like that all the time, and you still have to do the homework I assigned.
Now, one cool thing about the things that Newton studied with fluids is because he was one of the inventors of the calculus. He studied, like, and you could do this experiment at home, get a bottle of water and you poke holes near the top, near the middle, near the bottom, and the water will flow much more quickly out of the bottom than the top. So this is a way of studying a fluid dynamics things with a new type of math that had just been invented in 1666 or 1674, if you're talking about Leibniz.
I mean, I guess that makes sense that there's more pressure at the bottom, and so there would be more liquid or being pushed out with more pressure rather than at the top, right?
Yeah, it's all about the weight. Yeah, definitely. And
but we didn't really develop the math to describe that situation until Newton.
Yeah, and using just this, and also the study of how water flows through, like for example, if water's flowing from one container into another container through a small hole, the water will contract after it's left the hole into the new thing. So you can basically the water almost seems to be attracted to itself, and this is a very unintuitive, I think. So let's imagine you're in a giant swimming pool, and there's another swimming pool next door, and they're connected together by a wall. If somebody cuts a hole in the swimming pool and you go through, you're going to go through and then feel compression after you go on the other side for a moment. And this is the beginning of the formalization of fluid dynamics.
Well, Well, isn't that one of the properties of water that makes it so that we can even exist on Earth? That it's polar, right? That there's kind of there's like a negative end and a positive end of the molecule itself, and that's why surface tension is the thing.
Oh yeah, but I think that just has to do with the meniscus. Has to do with the vena contracta. I think it's what it's called, and it happens with any fluid that's going from one container to another. It causes like a compression after it's left the first container, seemingly paradoxically.
That reminds me of like heart motion, like fluid being pumped through your heart. That sounds familiar.
Oh yeah, the heart I think is one of those examples where evolution is a lot smarter than we are right now. I mean, you're only three cells away from a capillary at any point in your body.
See, we don't need to frighten our audience, Jonathan.
Well, too late.
We are talking about Newton and Bernoulli now. All the famous mathematicians. What could possibly be more terrifying?
The Bernoulli who studied a lot of fluid dynamics is Daniel Bernoulli, one of the many Swiss members of the Bernoulli family that somehow were all brilliant mathematicians. Don't know how that happens. But Euler, I don't know. Do you want to talk a little bit about just kind of the type of person that Euler was before we go into his work on fluid dynamics?
Well, I mostly know Euler from it's Euler's constant, right? I know E, that everybody's familiar with pi as an irrational number, the 3.14 on and on. That Euler's number is E, which kind of shows up naturally. It's actually the natural base. It comes up in mathematics, whereas pi kind of comes up naturally in circles and in geometry. Euler's constant E comes up in calculus and logarithms, and it just
unrestrained growth.
Yeah, and it comes up that there are certain patterns in nature that settle to E and things like that. So that's one of my favorites. That's probably my favorite number, actually, is E.
Yeah, and it's weird. The natural logarithm was actually invented before E was discovered, which I think is always weird. I think it was Napier who discovered it, or someone like that. But
so logarithm before exponential?
Yeah,
that's crazy.
Yeah, I mean, I think it was less than a decade between between the discovery of the natural logarithm and when they were using it to do slide rules. People were pretty desperate for fast multiplication.
Mm-hmm. That's awesome.
But yeah, Euler, one of my favorites, just to show you how much thought he put into things. When he was going blind, he'd have his nephews, who were probably very annoyed by him, do the writing part of his work for him, and he would fall asleep by calculating quartics. So, really interesting kind of guy. And he generalized the theory of fluids using partial differential equations. And we've talked a little bit about differential equations on other episodes, but I think it's good to do a little refresher since we will be talking about them for the remainder of this episode.
Well, before we get into differential equations, though, maybe we should talk about calculus in general.
Absolutely. Calculus was a branch of mathematics, glimpsed by Archimedes, formalized by Leibniz and Newton, and is used to this day in the study of almost all modern mathematics. Although avoided by many students due to the introduction of scary-looking symbols, calculus is a very simple field of mathematics with rates of change. A rate of change is anything that goes from one point to another. This can be over space, such as with hills, with time, such as with velocity. One common rate of change that we see every day is represented by the speedometer. When we're going at a constant speed, the needle does not move.
So calculus literally means, I was just looking this up, it literally translates to small pebble, used for counting and calculations like an abacus. So it's counting with very small things. And what's kind of interesting is that the concept of calculus went from infinitely many small pieces into something that's continuous, which I think is really beautiful. That was one of the first times I've ever felt like I understood in any way that a human being can understand it, but the concept of infinite.
Oh yeah, and that was what attracted me to calculus before I learned it. Was just I was a kid obsessed with the symbol infinity, and seeing limit x approaches infinity, which is part of calculus, just was that was fun. You could tell what kind of people we are because we think that kind of things are fun.
We do. They are. You don't know, but we're going to tell you. So there's two major branches of calculus. There's differential calculus and integral calculus. So we're going to talk about, so differential calculus deals with differentiation, otherwise known as derivatives. And then integral calculus deals with integrals, which that one's a little more self-explanatory. But let's talk about what a derivative is.
All right. So yeah, we definitely already mentioned that it's a rate of change with respect to another variable. But you brought up during the break a good example of a ladder.
So that's one of the more common, most hated problems in a beginning calculus course. If you think about a ladder leaning against a wall and it starts to slip along the ground so that it's falling, like dragging along the wall as it's slipping on the ground away from the wall, the ladder's shape doesn't change, but the velocity with which it's falling, or the rate of change with which it's falling along the wall, is a different rate than the rate that it's going away from the wall. So the change at the top of the ladder is actually a different rate than the change at the bottom of the ladder, and those are related by the shape of the triangle that it forms with the wall and the ground.
Yeah, so it's relating different rates of change. Yeah. Another example, I think that's that sort of shows a little bit of this kind of thing is when they built the pyramids, they got stone out of the quarries at a constant rate of change. So they didn't speed up, they didn't slow down. But because of the shape of a pyramid, it would have taken about 7/8 of the time to build the first half vertically of the pyramid, which must have been a nightmare for the people who were managing stuff for the overly demanding pharaoh.
Because first of all, you'd have to explain to him what 7/8, of the timeline would be. Nobody likes fractions.
Although it must have been very nice to see the pyramid go up very, very quickly during the last 3 years or so.
True.
But yeah, so those are derivatives is literally just a rate of change over any measure.
And the one that we're probably most familiar with is something like speed or velocity, where you have a change in distance over time. That, if I walk a mile over the course of half an hour, I'm going 2 miles per hour. So the rate of change is 2 miles per hour.
Now, one thing you said is over half an hour. Would you like to talk at all about what an instantaneous rate of change is, where you divide by an infinitesimal amount?
So that's essentially what calculus is, right? So my average rate of change, I walked a mile in half an hour. So my average rate of change is 2 miles for every hour. But occasionally I'm going to have to cross the street, which means that I'm going to be jogging to avoid whatever, driver is not paying attention to me. And there's going to be times where I lollygag because, hey, look, there's a butterfly. So the average rate of change is just the over the course of the entire trip. Instantaneous rate of change is how fast I'm going at any given moment. And that's what a derivative can calculate, is that instantaneous rate of change.
And if you'd like to know a little bit more about this, I suggest looking up the secant rule. It's basically saying if you get a stopwatch, you measure somebody's path, you click it faster and faster until you're clicking it infinitely fast, and then you get their instantaneous rate of change. But it's a little bit more formal than that, but we don't have time to talk about the secant rule.
Well, and what's kind of interesting, so a secant line is where you take, so any given function, so if you can just imagine some random curvy line, if you take two random points on that line and connect a line through them, that's called the secant line. And it's an estimate of the slope or of the line that function forms. And if you get those points closer and closer and closer together, eventually you'll get to what's known as the tangent line, which I think more of us are probably familiar with from geometry.
Oh yeah, if you put a book on a basketball, the lines that go on the surface of the book that touch the surface of the basketball are tangent to that basketball.
I think that's actually the technical definition of a tangent line, or that was the original definition, is it's a line that intersects a circle exactly once.
Oh yeah, and I think they appropriated it for more complex curves in the 1700s and stuff. That
sounds about right. I mean, it would have been Newton, right?
Oh yeah, Newton and et al.
So that's a derivative, rate of change over time. That one I think we can wrap our heads around, because most of us have seen slope in middle school and high school. We know rate of change, distance over time. The opposite of that, both in understanding it and actually calculating it, is much more complex. It's a fairly simple concept that an integral is essentially the reverse operation of a derivative. Instead of we're given velocity, and then velocity over time would be acceleration. It's your change in velocity over time would be acceleration. If we go the other way, velocity, the reverse of that, velocity over time, or velocity is distance over time. So the integral of velocity would be the distance.
Yeah, so your odometer is the integral of your speedometer. Or at least it measures the integral over time.
Dude, it never even occurred to me that my car could do calculus.
Another example of the integral is if you take the surface of the sea, subtract the sea floor from it. So you have this, basically the height at every point, and you take that integral with respect to the map, then you get the volume of the sea.
So the integral of the surface of the ocean
minus the sea floor.
That makes sense.
So anywhere you have an area, anywhere you have two things multiplying by each other. So if you have miles per hour times hours, you get miles. You get miles per second times seconds, you get miles per second. Don't know why I chose those units. It's very quick. Yeah, so the you definitely touched upon it, is that the integral is, like the opposite of the derivative. And if you take the integral of the derivative, you get the original thing back.
Well, in the most basic, and you actually inspired this analogy. So I think just about everybody knows velocity equals distance over time, right? So that, in my mind, is a derivative. So distance divided by time. If we multiply by time, then distance is velocity times time. That's essentially integration. That's the reverse operation, but it's still the same formula that we're talking about, just rewritten.
Yeah, so if you understand that division is the opposite of multiplication, then you will understand the fundamental theorem of calculus. There's a little bit more involved formally. For example, derivatives are one of those things that have closed form solutions basically all the time. Integrals can be very difficult or even impossible to solve using existing functions, which is very interesting. We don't have time to go into that, but it's a fascinating topic.
And oftentimes frustrating.
All the time frustrating. Besides pulling the ladder out from your friend and watching them fall, what's some applications of calculus?
Well, let's see. If we're talking mathematical applications or maybe physics application, calculus is kind of the foundation of science. It's really, and all branches of mathematics use it. It's almost like the higher level algebra, that algebra is a foundational mathematics for every other thing you're ever going to do. Just basic algebra is included in that, which I'm sure all of you out there are shuddering to hear that. But calculus is kind of it's like the algebra of higher level math. It's the foundational math that you need to know to be able to apply and analyze other branches.
In fact, in elementary school, you probably learned a little calculus without knowing it. Newton's first, second, and third laws, well, first and second especially, an object in motion will stay in motion, or an object at rest will stay at rest, is saying that the derivative is zero. That's all that's saying. Originally, he stated it using calculus, not English.
That's interesting that no one ever told me that in English. I know the laws no one told me the laws in math. You would have thought that me, a mathematician, they would have told me, but that's the first time I've heard that. That's interesting.
Yeah, and using what's called variational calculus, which we definitely don't have time to get into, you could solve problems like what's called the Birk-Histochrone problem. Basically, it's saying, imagine you have a flexible piece of cardboard and you're rolling a ball down it. What shape does it have to be so you could put it anywhere on the cardboard and it'll still take the same amount of time to reach the bottom? You could solve that using calculus. So you could do magic with calculus, basically.
Yeah. So remind me, what are the three laws? Because I think I remember them all.
An object in motion will stay in motion. An object at rest will stay at rest. So those two are the derivative. A closed system is zero. And the third law is about interacting bodies. Any action has an equal and opposite reaction, which is saying that the sum of all actions is zero.
So I definitely remember dealing with vectors when dealing with that law in physics in high school. So the third law. Okay, so let's talk about what a vector is. Before we transition into vector calculus, what is a vector?
One thing that you could definitely do is understand a vector. If you understand, just by the nature of being a human or a dog. Dogs are one of the only animals that understand symbolic vectors. Pointing. Well, pointing is part of a vector. You have a direction, but you also need magnitude. So let's say there's a point in space and it's windy at that point. The direction that the wind is going and the speed that the wind is going represents a vector. That's my example.
That reminds me, there's a character in the kids movie Despicable Me whose name is Vector, and he's very excited because I don't remember if he has it or he talks about having direction and magnitude, and he's very excited about it.
That's a hidden joke, apparently.
I love Despicable Me. So a vector. So let's see, an example of a vector. Like I said, most of my examples are in pure mathematics, which aren't super helpful. I know for sure that vectors are used a lot in air traffic, that the travel of planes and their trajectory is mapped by vectors.
If you throw a ball, the motion of that ball at any point in space is represented by a vector. So, I mean, if you have rate of change and that's happening in free space, that's a vector. So when we talked about derivatives, we talked about speedometer, but a speedometer is very flat. It just either 60 or 30 or 45 or whatever. With a vector, you have, unless it's a one-dimensional vector, which it can be, but you have multiple degrees of freedom. So if you're in a plane, if you're taking off, you're going vertically very slowly, but forward very quickly. So that's an example of a vector. And to add vectors together, you just use the Pythagorean theorem. They're actually quite simple.
Although sometimes that math can get really ugly really fast. It's interesting now that I'm thinking about it back to when I took vector analysis in college and any classes pertaining to linear algebra, that I always kind of thought of vectors as being fixed. And then when I took vector analysis, and that was no longer the case when we were dealing with things like vector fields, where there was a rate of change of not only direction, but magnitude of acceleration, basically, or velocity. The wind was changing speed. That blew my mind. That was really hard for the math for that was really hard.
You look at the fluids, which we're talking about today. I mean, the motion of people in Grand Central Station, the antivortices when they accidentally find their own pheromone trails, all this stuff can be modeled by vector fields.
That sounds like a lot of work.
Oh, absolutely. But yeah, and that's another good point about vectors, is that they're a building block. They're not a be-all and end-all. And so you could do things with vectors and calculus. Do you want to maybe get into gradients? Well, basically what a gradient is it points towards the steepest ascent or descent, depending on if you take the negative or the positive of the gradient. So if you're a mountain climber, you're interested in the gradient of the mountain because that's the way to get to the top the quickest, and I guess the most perilously in some cases. If you, you could see a gradient if you look at those altitude maps that have all the, you've probably seen them. They have a bunch of squiggly lines that represent different altitudes. If you connect the lines that are closest to each other, that those are the vectors that point in the direction of the gradient.
So what is the gradient kind of that's like the path of least resistance kind of thing?
If I think that's the path of least resistance when it's applied to a system of actions. But it's definitely the path of steepest ascent and descent.
So most efficient then.
Oh yeah, definitely in some contexts. Mm-hmm. And the reason why it's important is because, like we touched upon, derivatives are used for optimization. So when a derivative is zero, let's say let's say you're on a roller coaster and you're measuring your vertical speed. When your vertical speed is zero, you're either at the top of a hill or a bottom of a hill. And you can extend that to any number of things. So you can always optimize with derivatives. Not always easily, but you can always do it.
Well, one of the best analogies I have for the derivative being zero is if you think about throwing a ball in the air, it's kind of a parabola shape. It's got a curved shape. That there's a moment in space where the ball stops. and then it starts to fall again. So it's traveling up, and then for a moment, instantaneous moment, it stops and then begins traveling down. In that moment, the derivative of its motion is 0. It is no longer moving in that exact moment that's where it goes from going up to going down. It changes direction, and in order to do that, to go from a positive direction to a negative direction, it has to go through 0.
And the one-dimensional gradient is just called the derivative. Gradient is just extending it to multiple dimensions. So if instead of throwing a ball, like in the previous example, you're making your bed and you throw the bed sheet on, the point where the sheet is not moving is going to be, if you take the gradient of the motion with the height with respect to the motion, is going to be 0.
Oh, see, that makes a lot more sense than what they tried to teach me in vector analysis. Where were you 10 years ago, Jonathan? You were probably still in middle school.
I actually did not go to middle school. Fun fact.
How'd you manage that?
Oh, I read Goosebumps. It made me scared of middle school, so I just skipped right to high school.
I don't know that that's much better.
But moving on to the curl.
Move on to curl. What is curl, Jonathan?
How swirly things are. So you stir a cup of coffee. The curl is the vector that points towards the swirls. So it'll be a vector that's coming out or into your cup of coffee. And that's an eddy is an example of a curl, or a vector, or where a curl vector would show up. It's just a way of measuring swirliness, which has obvious applications in the mathematics of fluid dynamics.
Well, what are those applications, or why do we need to know the measure of that vector?
It has to do with because as we're gonna talk a little bit about Eulerian and Lagrangian fluids in just a little bit, but basically you have to deal with these parcels of water that move around, and if it's going towards a wall, for example, it's going to flatten out. And just like in the latter example, you have a non-uniform motion. And anytime you have non-uniform motion, you have curl. It's also the same principle why electricity traveling through a wire deflects a compass, because you can measure the wire. In this case would be the curl of the magnetic field, I think. But that's a little bit of a contrived example.
The example that's coming into my head of why this is important, like why we care about this, is something along the lines of dealing with getting fluid from one place to another. So something like an oil pipeline, or something like even just plumbing in a residential area, getting water to a residential street. That requires a fair amount of mathematics to be able to do that in a way that's safe.
Yeah, the Romans were an example of they thought that doubling the size of a pipe, for example, of an aqueduct, would double the amount of water that went through, and somehow they managed to build an empire. But if they knew the curl, they could have done things a lot more efficiently with their and anytime you want to change direction, you're going to have to deal with the curl. And when you're dealing with turbulence, which is what happens when you you see turbulence all the time. You look at clouds; those are an example of turbulence. You have to deal with the curl.
Well, and I know that once you get to a certain point in engineering, or when you're going fast enough, that you no longer treat air as like the way that you calculate how you move in air becomes a fluid calculation. That you're moving fast enough that air becomes similar in the way that it interacts with your object as it does in fluid.
All of these examples have to do with just the study of torque, which at this point in time, when the curl and things were being developed, was a very new. It replaced the law of simple machines, basically. So these are reasons to care about. These are the reasons why we need to know about the curl. If you're measuring something as swirly as liquid or gas, you're going to need to know how to measure that swirliness.
That sounds funny. I hope that that's something that is said in graduate level mathematics courses. Let us measure the swirliness.
Swirliness 235.
Yeah, is there a scale of swirliness? Is it like from 1 to 10 or?
Well, I think that if the radius approaches zero, it gets infinitely swirly. That's a technical term.
That makes
Infinitely
sense.
swirly.
Infinitely swirly.
We only have a couple more things about vector calculus, and bear with us. And we're gonna just go through them very quickly. We have divergence. And that's important because if you've ever opened a door and then the door slams closed, you notice that there's a difference in pressure outside of the room and inside of the room. So you could model that as what's called a source or a sink, which it was literally named after the sink that you wash your hands in by Maxwell in his treatise. So a sink is something that sucks out fluid, and a source is something that inputs fluid. And you measure how much that is inputting or outputting using what's called the divergence.
I do remember learning the divergence theorem. I don't remember what it is, but I do remember learning it in both vector analysis and the physics part 2.
Here's a way of explaining the divergence theorem. Let's say you're in a closed room with a bomb. The bomb is going to be a source of air. It's going to explode and it's going to add a lot of air to the room. So it's going to be a source. If you measure the pressure in the entire room, it's going to all increase because of the bomb exploding. So the sum of all sources and sinks in a region, like a volume, gives the net flux out of a region. So if you open a window, air is going to go out that window when you explode a bomb. And that's the divergence theorem.
I mean, I don't think I'm going to be real worried about the divergence theorem if I'm in a room with an exploding bomb, but, for later when my ears stop ringing.
And finally, we got the Laplacian, which is kind of like it's kind of the opposite of the gradient. It's actually the divergence of the gradient. Don't think about that too hard. If you take the Laplacian of a hilly area, it's going to be positive on the top of the hills and negative on the valleys. And that's what that is. And the reason why we're illustrating these concepts so quickly is just to show you that vector calculus is accessible. It's not magic. It's not something that's unintuitive. It's something that you have the hardware to understand already. And all you need to know is the silly little symbols that go along with it.
And I do really wish that we had had this conversation 10 years ago when I took vector analysis. That I feel like I would have understood it a lot better had I been able to talk about it in these words first.
YouTube has been a godsend for just my understanding of especially the Laplacian.
I don't feel like there was a lot of Laplace on the YouTube when I was back in my day, unfortunately for me.
After a few centuries of mathematical inquiry and development of calculus, and in particular vector calculus, theories of fluids abounded. Whether it was Euler's description of fluids as a field of vectors, or Lagrange's description of fluids as a set of deformable packets, significant advances in fluid mechanics were made in the 17th and 18th centuries, with the solid foundations of the principles of friction, viscosity, and other properties of fluids, the Navier-Stokes equations, which are used every day for things such as studying ocean currents, weather modeling, and hydrofoil and aerofoil design, began to take shape. And it all started with one remarkable man, Jean-Claude Navier.
So it strikes me as interesting. We were researching Navier for this episode, and I didn't really know anything about him. And we went to look him up, and of course, we went to Wikipedia because Wikipedia is the best. And there were what, 2 paragraphs about him?
Something like that. It was basically a stub.
It was like, hey, this guy was born, and then he died, and he worked with Stokes.
And his name's on the Eiffel Tower, along with 71 others. That's pretty much it.
And he was born in
page.
Dijon.
Yes, like the mustard.
But basically nothing else. And so we looked up, we found just the trick of Jonathan's that I didn't actually know. That if you look up an article in the native language, so Navier is obviously French. So we looked up the French article and then it translated it for us. There was way more to go off of there.
Good study tip if you're studying anything from any other country, especially studying German philosophy, check out the German page, etc. But we are studying the French page. And he didn't just study fluid mechanics. He studied elasticity. He was famous for building things, right?
Yeah, he was. Well, that's why his name is inscribed on the Eiffel Tower. He's supposed to be one of the kind of the founding, I guess, developers of bridges.
Basically, he made bridge building in a very big sense possible. So he understood that there is elasticity and deformation, what's called soft body dynamics versus hard body dynamics, existed.
So this guy was actually incredibly prolific in his life's work. On the French page, he is referred to as an engineer, mathematician, and economist. So he worked with some really just well-known mathematicians. It's impressive to me that Navier is not one of the mathematicians that is as well-known. He worked with who was his advisor? It was
Fourier, who you'll appreciate if you're listening to this at all, because MP3 compression relies on Fourier's theories.
He worked with Cauchy. He corrected something of Galileo's. He worked on the work of Laplace. Like, he was prolific. He worked on everything and made meaningful contributions to them.
Yeah, Amy described him as a 18th century Erdős,
who we talked about on one of our previous episodes.
Yeah, so basically what he did was he took Euler's and Lagrange's fluids, which only really work in imaginary land, or when you're talking about liquid helium, these mysterious fluids that just flow forever, that have bizarre properties, that have no meniscus being the a product of surface tension. When you fill up a glass of water, it curves up at the edge. That's the meniscus. None of that was modeled before Jean-Claude Navier, at least not very rigorously,
and not in a way that was in any way helpful or meaningful.
And Navier's equations they're called the Navier-Stokes equations because of Sir George Gabriel Stokes, who we'll talk about in just a second. But Navier was the idea man behind that, although Stokes, in his own right, was a brilliant human being.
Agreed. So Stokes improved on Navier's analysis by inserting a different explanation for the internal friction of fluids, making the derivation of the equation more credible.
Yeah, he took what was basically intuition and found the core of it. It's I think it's a lot like Galileo with he observed that the period of things of the same length is equal. So if you swing one of those incense burners back and forth, it's going to have the same period. That he didn't do that with calculus. Newton and Leibniz and et al. Did that with calculus. So that's what Stokes basically was. And Stokes did a lot of stuff with optics too. He was a polymath of the highest degree too. So one thing that you might wonder is these equations have, like, Navier did a presentation on them in 1822, 14 years before his death. Why has it taken centuries to understand and not even completely understand these equations?
Well, as I recall, they're pretty awkward. There's a lot of variables in them. There's a lot of coefficients in them. There's just a lot going on in the equations.
It's like a grocery list. You know all the individual things that go into it. You have to buy 2 pounds of flour. You have to buy pasta. You do have all these things, but just giving somebody a grocery list does not tell you, for example, the type of diet that they're on, or it doesn't tell you that they dislike chocolate more than caramel, but chocolate was on sale. There's a lot of nuance that comes from these equations because they are, as we touched on earlier, nonlinear. And why is nonlinearity difficult to solve?
Well, I mean, we're talking about so many different, it's almost chaos, right? If we're talking about fluid dynamics, that it's borderline impossible to model it that specifically, that exactly, I think is probably the right word. Nonlinear definitely makes it much more complex.
Oh yeah, if you look at turbulence, which, as we said, happens when you have clouds or when you're swimming in water and you kind of feel if you switch your hand through water real quick and you feel your hands vibrate, that's turbulence. And turbulence has been shown to be extremely dependent on initial conditions and what's called Reynolds numbers. Reynolds numbers describe how fluids act in certain situations. For example, vortices created by wind passing a pole. So you have, clouds are part of the fluid dynamics equations. Pouring a glass of water and seeing it stay in the cup is part of the fluid dynamics equations. All of this is part of the fluid dynamics equations.
So you said earlier that Feynman said that turbulence is the most important unsolved problem of classical physics. Why is it so important, do you think?
I think it's so important because, I mean, you run into turbulence practically when you're designing, like we said, airfoils, things like that. It's unpredictable, and any unpredictable system that shows up as frequently as turbulence does. I mean, as my day job, I develop algorithms that rely on simplified models of turbulence to get solar panels to stay on roofs. And if we knew how to do that more efficiently, we could do that cheaper. I mean, that's just an economic reason, but there's a philosophical reason too, I guess, which to me is more interesting.
The millennium problem approach of, solving something that's difficult for the sake of it, for the pursuit of mathematics.
And that's one thing that makes it especially difficult to solve, is that it's not very well defined. The whole problem boils down to figure out what the Navier-Stokes equations do, simplify them so that computers or whoever can understand them better. It's very ill-defined, and that's one of the major challenges. So one thing I think we should talk about is what would, not just what the solution to the Navier-Stokes equations do for us, but what it might look like. Because obviously we already have the equations, so what would a solution look like?
I don't even know if we could find a solution unless we can define the question better or define the equations better.
Yeah, I think that it would have less variables because, I mean, the Navier-Stokes equations, you have viscosity. I mean, if you've ever played with cornstarch and water, that's a highly non-Newtonian fluid. We didn't even talk about Newtonian fluids, but you press down on cornstarch and water and it turns solid. You stop pressing and it turns into a liquid. You could model that using the Navier-Stokes equations. So they're extremely complicated, and it's not even clear that a solution exists that's more simple. So it's like a lot of the millennium problems, like the P equals NP problem, whether or not computers can solve difficult problems more quickly than they currently do. All these problems are research problems that would take any PhD, possibly they have taken PhDs lifetimes to not solve.
Or not solve, right. Well, and maybe the next step in the Navier-Stokes is to kind of define parameters, not necessarily to even clearly define it in the most general sense, but to be able to define it better given certain conditions or certain situations.
It would also, if we had, and the heart of any theory is predictability, really. The theory of, for example, the conservation of energy means that you can see how fast a ball how fast a ball needs to roll down a hill to go around a loop-de-loop, using some very simple things, which would it's a predictive thing. And as we've seen recently with the devastation caused by the hurricanes in Texas, Puerto Rico, and other places, if we have a better way of predicting when these things might happen, we could literally save property and life.
I always find it interesting when we can connect things back to what we've previously spoken about, and weather research is something that comes up. I mean, the discussion is always in chaos theory, that our entire world is a chaotic system. And it's interesting, or I find it exciting, that maybe the Navier-Stokes equations can be a bridge to across that chaos, as it were.
Fluid mechanics is an interesting field that can claim discoveries being made every year, but a set of 300-year-old equations still continues to baffle the world's greatest mathematicians. But every year, the world is getting more educated and less poor. Sooner or later, some mathematician will be struck with inspiration, such that he or she will have solved the Navier-Stokes equations satisfactorily, and we'll be stuck with a new super hard problem, or at least one that isn't currently defined as one of the 6 that will get you $1 million each. I'm Jonathan Baca.
And I'm Amy Lynn.
And this has been Breaking Math. We'd like to give a quick thanks to Brilliant.org for sponsoring us. We genuinely love their content. all of us here are users of the site. Anything you'd like to say about Brilliant.org?
It's just a super fun app and website. Check it out.
And if you'd like to directly support the show, you could do so by going to patreon.com/breakingmathpodcast. Just the price of a cup of coffee, which you stir using the Navier-Stokes equations, will get you advanced access to episodes when we have them. And if everybody donated just $1, it'd be enough to keep the show not only going indefinitely, but it would become a primary job for us. And that would be amazing. So thank you for listening. And until next time, row, row, row your boat gently down the stream. Merrily, merrily, merrily. Navier-Stokes aren't what they seem.